Welcome everyone. In this video, we continue Module 4 of Fundamentals of Artificial Intelligence. So in this video, as I said, this is our fourth module and we have these many contents like definition of classical planning, algorithms for planning with state space search, planning graphs, other classical planning approaches, analysis of planning approaches and hierarchical planning. So in this video, we will mainly focusing on hierarchical planning and analysis of planning approaches. Hope all other concepts are clear to you. So as we discussed earlier, planning is one of the most important capabilities of an intelligent agent. Without planning, an agent can only react. With planning, it can anticipate, reason, and act purposefully. So, mainly, we will understand why hierarchical planning is needed and study of HTN in planning. And then we will examine algorithms and correctness properties. And then finally, we will analysis the different planning approaches from a computational perspective. So planning is a course of action, which is a key requirement for an intelligent agent, the right representation for actions and states, and the right algorithms which can make things easier. So formally, we have a state space, a set of actions with preconditions and effects, and then a final goal. The planner's task is to find a valid action sequence. So, planning is deciding what to do and in what order the plan has to be executed. Now we'll see what is hierarchical planning. So this is a main idea in which it attempts to manage the complexity. For example, complex software is created from a hierarchy of subroutines and classes. Armies, governments, and corporations have organizational hierarchies. So, as problems grow, the number of states increases exponentially, and also the number of plans or number of possible plans becomes enormous. So, hierarchy is a controlled strategy. So, the key benefit of hierarchical structure is that at each level of the hierarchy, a computational task, military mission, or administrative function is reduced to a small number of activities at the next lower level. Okay, so the computation cost of finding the correct way to arrange those activities for the current problem is small. For example, if you're considering a simple example, an army commander gives high-level orders, not individual soldier moments, right? So now we'll see what is the main idea behind hierarchical planning. There are mainly three things, that is high level actions, searching for primitive solutions, and then searching for abstract solutions. So hierarchical planning separates high level planning and low level planning. High level planning means that what to do, low level planning is how to do it. Okay, so high level actions are later refined into more detailed actions. This mirrors human reasoning. For example, if you are considering an example like you decide that you are going to decide that I will prepare for exams. So after that only you will decide which subject to choose first, which chapter, and on which day should I study this subject and which chapter. The basic formalism we adopt to understand hierarchical decomposition comes from the area of hierarchical task networks or HTN planning. Hierarchical planning is mainly formalized using hierarchical task networks, that is also known as HTN. So there are some key assumptions behind it, that is environment is fully observable, and then actions are deterministic, actions have preconditions and effects. And we have new high level actions, and these represent the abstract task that is not executable. For now, we assume full observability and determinism and a set of actions now called primitive actions with standard precondition effect schemas. For example, instead of planning everything in tiny steps, we think in big actions first and break them down into smaller action, and finally then break into primitive actions, which the system can directly do, right? So high level actions means that here high level action is a big task, okay? It can be considered as a big task. For example, in this slide, it is written that go to San Francisco airport. So this is not a single step, right? It's a big goal. So you have to refine it, or you have to break down into different parts. So each and every big action can be refined or split into smaller actions. So in this case, go to San Francisco airport. This can be broken down into from home, go to San Francisco airport. That is your option one. Then you have next one, go from home, you take bus and then go to airport and then from there to San Francisco. So the same goal can have multiple ways or refinements. Okay. And finally, you have primitive actions. Primitive actions are the very smallest actions that cannot be broken further. For example, walk, take bus, drive, turn left, stop. So these are the actions the agent can directly perform. And again, you have recursive refinement, which means that you don't jump directly to tiny actions. You will break into medium steps, then break those into again small steps until primitive actions only remain. Okay. So, in order to reach a destination, what you will do? Take a step, then take another step, and finally, you will reach your final destination. So this slide represents HLA, that is high level actions. So it is given that go home, comma, SFO. So go from home to San Francisco airport. Okay, that is your high level action. So you have around 5 refinements. The first refinement is your direct step. That is from home, you can go to San Francisco. And you have 2 steps, that is drive from home to the airport parking and take a shuttle from parking to the terminal. So you have to do 2 actions, that is drive and shuttle. And now in the second refinement, you can see that taxi home, comma SFO. That is, this is another way to go. That is, just take a taxi directly. So same goal, right? From home, you can go to SFO airport with the help of taxi. So this is your second refinement. And now you have some rules, okay? That is navigation rules. So first refinement navigation rule suggests that if you are already at the destination, no steps are needed. That is navigate A, comma A, then you don't do anything. Okay, if you are at the say destination or if you are at the SFO airport, then you should not do anything. And after that, next recursive refinement is that again navigation rule. That is, if 2 locations are connected, you move 1 step left or to the right and then recursively navigate again. So that is what written in fourth and fifth refinement. So if 2 locations are connected, you move 1 step left or to the right, then recursively navigate again. So this model suggests that take a step, then take another step and take another step until you reach your final destination. So the outline or the summary of this program is that one high level goal you have, that is go to SFO, and this can be refined into multiple methods. So you have navigation rules, that is also defined in a recursive manner. So planning continues until only the final primitive actions remain. So the above examples show that high-level actions and their refinements embody knowledge about how to do things. For instance, the refinements from go home, SFO say that to get to the airport, you can drive or take a ride-hailing service. Buying milk, sitting down are not to be concern. So HLAs can be refined recursively. A refinement may contain two things, that is primitive actions and HLAs. So this forms a tree-like decomposition structure. So for example, if you're considering a simple example, like in order to build a house, what you should do? You should build rooms. So in order to build the rooms, you should lay the bricks and as well as you should paint each and every walls. So same structure repeated at different levels. For different rooms, you should repeat these steps. An HLA refinement that contains only primitive actions is called an implementation of the HLA. When a big action, that means HLA, is fully broken down into only one basic actions, that final sequence is called the implementation. For example, HLA is equal to go, home, comma, SFO. So it can be refined to walk, then board bus, and then get down. So these are the primitive actions. So this is a example for implementation. So in a grid world, the sequences right, right, down and down, right, right both implement, then HLA navigate. So suppose you are at the point 1, comma 3 and you want to go to 3, comma 2. You have two valid ways, that is right, right, down and down, right, right. Both are correct implementations of the same high level. So you have same goal but different paths or steps. So an implementation of a high-level plan is the concatenation of implementations of each HLA in the sequence. So if your plan has multiple HLAs, HLA 1 is that go, home, comma, bus stop. And next HLA is or plan is that go, bus stop, comma, college. So then you have the implementation as steps for first HLA plus steps for HLA 2. So you can join all the primitive steps into one long action sequence. So using the precondition effect definitions, we can check if plan achieves the goal. So we look at the preconditions as well as the effects. Preconditions means what must be true before the action, and effects means what comes true after the action. So by applying them step by step, we can then verify that does the sequence finally reach your goal state. So we can tell that implementation is a refinement of a high level action into only primitive actions, and a higher level plan works if its combined primitive actions lead to the final goal. So we can say that a high-level plan is considered successful if at least one of its possible detailed executions reaches the final goal. Not all of them must succeed, just any one is enough. That is written here. The at least one in this definition is crucial. Not all implementations need to achieve the goal because the agent gets to decide which implementation it will execute. So a high-level plan achieves the goal if at least one of its implementation achieves the final goal. Okay. For example, a high-level plan like go home, comma SFO can be executed in different ways with the help of taxi, bus, or drive plus shuttle. So if any one reaches SFO, then the plan is considered as valid. So you do not require every possible method to work. Only one method needs to work. So HTN planning is more relaxed than strict plan. So the system, or you can tell like agent, can choose only one method among many. Any one possible solutions should work. This is not like non-deterministic planning where you must handle all the possible outcomes. When HLAs have multiple possible implementation, there are two options. That is, one is to search among the implementation for the one that works, and the other is to reason directly about the HLAs despite the multiplicity of the implementations, which means that you have to try different detailed plans and see which one works. For example, your goal is to go to college. And then you have possible implementations like you can take bus, auto, bike, or walk. So what you will do, you will test or search among these and pick the one that works for you, right? So that is what searching among the implementations. And next one is reason at the high level, that is about HLAs. So we will not go into all the details, think only in terms of the big actions. So instead of checking walking step by step or best step by step, you reason like going by bus will reach the college. Next is searching for primitive solutions. HTN planning is often formulated with a single top level action called ACT, where the aim is to find an implementation of ACT that achieves the goal. This approach is entirely general. So this means that HTN planning can be written using one big action called ACT, in which it is to find a sequence of primitive actions in order to reach the goal or in order to achieve the goal. Okay, so we create one main task and we have one goal and we refine it until we get only primitive actions. So classical planning problems can be refined as refinements of act. Each primitive actions like move, pick up, drop is added as a refinement of act. So act can be primitive actions, comma, act. So act, what are the different actions you can take? That is, you can move or act. So do one action, then continue the planning. So, and act keeps calling itself again and again. Do one action, then again do another action, and likewise another action. So take a step, then take another step, and then take another step until you reach your final goal. But we need some way to stop the recursion, right? So we do that by providing more refinement for ACT, one with an empty list of steps and one with a precondition equal to the goal of the problem. This says that if the goal is already achieved, then the right implementation is to do nothing. That is, if you're already at the destination, you don't need to walk anymore. So if, for example, if you're already in the class, then do nothing. So the approach leads to a simple algorithm. Repeatedly choose an HLA in the current plan and replace it with one of its refinements until the plan achieves the goal. One possible implementation is based on the breadth first search tree as shown in the next slide. So in this slide, we can see the hierarchical planning algorithm used in our classical planning. So as we discussed, hierarchical planning breaks a complex problem into smaller sub-problems using different abstraction levels. So instead of solving everything at once, we'll start with high-level actions, that is the abstract task, and then you can gradually refine them into detailed primitive actions. So we discussed everything, right? So now we'll see this algorithm. So you can see the function as hierarchical search problem, comma hierarchy. So in this case, it tries to find a valid plan using a hierarchical decomposition. So the final output is that it is a solution plan. Okay, you can see that frontier, that is the FIFO queue. FIFO is first in, first out, like breadth first search. So the frontier contains plans that still need exploration. What are the things or nodes which we need to visit, or which are the plans that we need to explore further? So what is a plan? A sequence of actions which you are going to perform. That is, it can be primitive actions or high level actions. High level actions needs what? Refinement. And next one is, and also high level actions are abstract actions. Okay. And now we can see the initialization with the Frontier. That is Frontier FFOQ with act as the only element. So we are starting with the initial abstract plan. For example, if your plan is the goal action. Okay. And next one is while true do. That is the main loop. Okay. And next one is if is empty Freunde, then return failure. If nothing is left to explore, then planning is failed from our side. And now you're going to select your next plan. That is plan pop Freunde. Take the next plan from the queue because in the FIFO, breakfast exploration is happening. So next one is you have to choose HLA. The first HLA in plan or null if none. So we are going to look for the first level action which needs the refinements and it has two cases, that is no HLA found, and next one is HLA exist. Okay. And next is you have to expand the plan. Expand the plan means replace HLA with the refined sequences. Okay. That is what you can see in add append prefix comma sequence comma suffix to Freund. This means that keep actions before HLA, insert the refined sequence and keep the remaining action, that is your suffix. So add new plan back to the Freund. So, in short, if you are telling that about the working of this algorithm, you are starting with an abstract plan, and then from that you are moving to your next stage, that is pick plan from the queue. And if there is any HLA, then you have to refine it into smaller plans. And you have to add the new plans or the new smaller plans to the queue. And if no, check if the goal is reached. And if it is returns yes, then that is the solution. Okay. And if it is no, then you have to continue the searching. So in the hierarchical planning, planning is increased gradually. Instead of exploring different types of primitive steps, it explores the higher level feature first. This form of hierarchical search explores the space of sequences that conform to the knowledge contained in the HLA library about how things are to be done. A great deal of knowledge can be encoded not just in the action sequences specified in each refinement, but also in the preconditions for the refinements. So, as we discussed, hierarchical planning is a method where a complex task is solved by breaking it into smaller and more detailed steps. So instead of searching through all the possible actions randomly, the system uses high level actions called HLAs, which represent the abstract task. These high level actions or HLAs are gradually defined into lower level actions until we get a primitive action. So, mainly this approach explores only those action sequences that follow the knowledge stored in the hierarchy, and expert knowledge about how tasks can be done is encoded into the planning processes. So, the refinement rules also include the conditions that must be satisfied before breaking down a task, which helps guide the planning more effectively and efficiently. So, because of this structured approach, hierarchical task network planners can generate large and complex plan while performing very little search compared to the traditional planning methods. The key to HDN planning is a plan library containing known methods for implementing complex high-level actions. So instead of solving each and every problem from the beginning, the system can use known high-level actions and also the predefined methods in order to break the task into smaller steps. For example, if you are considering a situation in our real life, so when we plan for a trip, we don't think about every small action immediately, right? First, we decide to go on a vacation, then we refine it into smaller tasks like booking tickets, packing bags, and arranging the transportation. Similarly, in the case of HDN also, it plan learns from the past problem solving experience. So once a good plan is created, it can be stored in its library and can be reused later. So one another example is that cooking. Instead of figuring out each step every time, we follow a recipe, right? The recipe acts like a stored method that breaks a high-level task like prepare a dinner into detailed steps such as cutting vegetables, cooking, and serving. So, as more methods are added, the system becomes more efficient and capable because new plans are built using the existing knowledge which is there in the library. So, in this way, the agent can become more and more competent over time as new methods are built on top of the old methods. One important aspect of this learning process is the ability to generalize the methods that are constructed, eliminating detail that is specific to the problem instance and keeping just the key elements of the plan. This means that instead of storing every small details, the system keeps only the important steps or the structure of the plan. Okay, the unnecessary details like names or locations are removed so that the method can be reused in another situation. So, for example, if you're considering like how to build a house, okay, on a specific plot land, so they don't need to remember the exact address or builder's name, right? Instead, what they will do, they remember the general steps like designing, then getting the materials, construction work, and how to finish it. So these general steps can be applied to all the building purposes or the construction purposes, right? So this generalization makes planning more efficient because the system can reuse the learned methods instead of solving every new problem from the beginning. The hierarchical search algorithm in the previous section refines HLAs all the way to primitive action sequences to determine if a plan is workable. So in hierarchical planning, the algorithm keeps on refining the high-level actions each step by step until they become primitive actions that can be directly executed. So, normally, in all the cases, the algorithm fully breaks down into tasks into detailed steps before checking if the plan will work or not. So, in the real life also, we often know whether a high-level plan makes sense even without deciding every small detail, right? For example, if you are planning to go to an airport, we may decide the main steps like driving from home to long-term parking and then taking a shuttle, right? We don't need to decide the exact route or parking spot immediately to know that the plan is reasonable. So the solution is to write precondition effect descriptions of the HLAs just as we do for primitive actions. From the descriptions, it ought to be easy to prove that high level plan achieves the final goal. So to make hierarchy planning more effective, we describe high-level actions using preconditions and effects, and this will help us to verify whether the plan can achieve the goal or not. So in short, this approach reduces the search space significantly because we work with the abstract plans, right? First we will work with the abstract plans and then we add the details each and every steps. For this to work, it has to be the case that every high-level plan that claims to achieve the goal does in fact achieve the goal in sense defined earlier. So the thing is that it must have at least one implementation that does achieve the goal. So in order to work with hierarchical planning, every high level plan must truly lead to the goal. Okay, this means that if a high level action claims to achieve something, then at least one detailed implementation of the action should actually achieve the goal. So these things are discussed in the previous slides. So in simple words, you can tell that a big plan should still work when we break it into smaller steps. For example, if we say that we are going to the airport, there must be a real way to do it, like driving, taking a taxi, or you can use some bus. Otherwise, the high level plan is not valid. So if high level descriptions are correct and realistic, then the planning process becomes very easy and more reliable. Given these definitions of hierarchical planning, a high-level plan is a sequence of HLAs in order to achieve the goal if its reachable set intersects the set of goal states. Okay, and conversely, if the reachable set does not intersect the goal, then the plan definitely does not work. The figure in the next slide will illustrate all these ideas. In this diagram, you can see how hierarchical planning will work using reachable state. So each dot represents a possible state of the situation. So the purple shade area represents the goal state, the destination or the final destination in which you want to reach. So in the first figure, that is A figure, the planner explores the possible paths from a starting state. The shaded dashed area you can see now that shows the set of states reachable through a high level action. Whereas in the case of part B, there you can see when the high level action is refined into more detailed step, new paths will appear. Okay, that red markings. The black and red arrows show different possible refinements or the sequences of actions that it can perform. So the main idea is that the reachable set is of states from the refined step must intersect with the goal area. If at least one refined path reaches the goal, then you can say that the high level planning is valid. For example, if you are considering this in the case of a, real life example. So each and every dot is the location you could reach, but the purple box is the airport. That is your goal state. So a high level action like go to airport represent many possible outcomes, right? Or many possible routes. So if at least one route actually reaches the airport, then you can say that your hierarchical planning plan will work. Now, in this diagram, it clearly explains the goal achievement for higher plans with the approximate descriptions. That is high-level descriptions. Okay, so each dot represents a possible state, and the purple box represents the goal region, as we saw in the previous image. The shaded areas show sets of states that can be reached using different plans. In the first case, that is A part, you can see the two possible plans. The black arrow, it shows a plan that definitely reaches the goal because its reachable area overlaps with the goal region. And the red arrow, you can see a plan that looks promising at a high level. But when we look closer to that, it may not actually reach the goal. Okay. And whereas in the case of part B, you can see we will refine the plan further. After refinement, what happened? We can realize that some high level plans that seemed correct earlier may not truly achieve the goal. So the main idea behind this is that high level planning gives us an approximate direction, but detailed refinement is necessary to confirm whether the goal can be achieved or not. Okay. So, if you are planning for a trip, you can tell that you are taking a public transport and it looks like a higher level, but detailed checking may reveal no direct route exists. So, that is one of the examples for this one. So now we'll move on to the analysis of planning approaches. Till the previous slide, we saw the hierarchical planning in detail. In this case, we are going to discuss about analysis of planning approaches. That is, planning combines the two major areas of artificial intelligence, that is searching and logic. So searching, as you saw in your second module, that it explore all the possible sequence of actions. For example, you might have studied about BFS, DFS, A star, AO star, and all. So that is a type of searching technique. Next one is logic. That is, it represents the normal knowledge in a formal way, and it reasons about the actions and outcomes. So planning is a combination of both searching and logical reasoning. So a planner can be mainly viewed as two types, that is a search algorithm looking for a solution path, or you can tell that it is a system proving a solution exists using some logics. So the planning problems are like a small toy problems, and this can be applied to different applications like robotics, logistics, industrial automation, and large scale decision systems. Now we can see the analysis of planning approaches one by one. First, you can tell that planning controls is a combinatorial explosion. That is, the biggest challenge in AI planning is that there are too many possible states and action combinations, right? If there are n prepositions or facts in a domain, then you have total possible states as 2 raised to n, because each proposition can be either true or false. For example, if you're considering a robot, it is at location A and the door is open and light is on. Okay, so there are three propositions and you have the possible status 2 raised to 3. That is 8 states you have. Okay, so in this real world problems may have hundreds or thousands of propositions. Like, so in the real world cases, there will be huge space, search space. So this type of problem is known as combinatorial exploration. Okay. And the second top point is that independent subproblems reduce the complexity of problem. So identification of independent subproblem is the main part. If parts of the problem do not affect each other, then you can solve them separately. For example, uh, instead of planning everything in a single manner, you can navigate the planning and then object manipulation planning also can be done. So if it is independent, you can solve separately. Next one is decomposability gives exponential speed up, which means that if a problem can be broken into independent parts, then search space will be obviously smaller and planning speed will also increase. Okay, this is why we mainly focus on hierarchical planning. Next one is negative interactions destroy the decomposability. That is, sometimes sub-problems will interfere into the another problem. That is, opening a door requires removing an obstacle, right? So moving the obstacle blocks another task. So sub-problems are not independent. Then you can see a SAT plan, right? That is planning using SAT solving. This represents a logical satisfiability problem. Okay, and this captures the logical relations between the subproblems. And also, we saw forward search with heuristics. That is, you will start from your initial state and you will apply actions step by step, and then you will use some heuristics in order to guide your search. So, unfortunately, we do not have a clear understanding of which techniques work best on which kind of problems or use cases. So, no single approach dominates. That is the conclusion of our analysis of planning approaches. So, modern system use the portfolio planners, parallel planners, and adaptive selection. So, you can tell that this all reflects the complexity of the real world planning, that quite possibly new techniques will emerge, perhaps providing a synthesis of highly expressive first order and hierarchical representation with the highly efficient factor and propositional representations that dominate today. In this fourth module, we study definition of planning, different classical planning approaches or different classical algorithms for planning, and then finally we concluded with analysis of planning approaches. In this module, we mainly discussed about the planning algorithms like forward state space search planning algorithm, and backward state space search planning algorithm, then hierarchical planning, then conditional planning, graph-based planning. So hope every concepts are clear. So this concludes module 4 of Fundamentals of Artificial Intelligence course. Thank you.